How you guys doing today? It's been an awesome SREcon. It's been very stimulating, learned a lot. Not over yet, and some fun tonight. So thanks for coming to hear us talk about Zero Trust networks. As you mentioned, my name's Evan, and this is Doug here. We're both SREs. We met working together at PagerDuty. Doug's coming from a primarily software development background, and I hail from a primarily network engineering background. Right now, Doug is SRE at Stripe, and I am unaffiliated. I left PagerDuty a few weeks ago to focus on this Zero Trust work full-time for a little bit. We both joined PagerDuty, as we call PD, within a couple months of each other. At that time, PagerDuty was still pretty young. I would say, I don't know, 20 people or so, 16, 20 people. Also, infrastructure is still fairly small at that time. But before going too much further into Zero Trust stuff, I think it makes sense to talk a little bit about PagerDuty's business needs and infrastructure needs. So I'm sure that, I'm not even going to ask, because I'm sure that everyone in this room knows who PagerDuty is. So as you know, it's really important to have high availability on the PagerDuty service. The whole intent is to minimize downtime for our customers. If we're down when our customers are down, we cannot affect our ultimate goal, right? So service reliability is really, really core to the PagerDuty business. And as much, PagerDuty is hosted in multiple cloud providers and geographic regions itself in order to kind of meet those goals. Each one of these dotted lines represents a boundary between a geographically disparate region or provider. And even though when we joined, the infrastructure is still pretty small, this kind of property made it challenging to operate. So all the clusters that we ran were all active in every region. And there are lots of third-party networks between these regions because there's just commodity internet, right? So this presents like a really, really large security challenge for us. You have to provide access control and confidentiality across the majority of flows occurring within the PagerDuty network. And so lots of problems to tackle, you know. We chose to kind of automate access control first. Essentially, we're just looking for security groups, right? That's all we really wanted. But security groups are AWS specific and they're region specific as well. So we needed like the same functionality except cross-cloud and cross-region. So what we ended up doing was built some kind of heavy lifting iptables automation inside of Chef. And what this did was it provided security group like semantics, except it was calculated by Chef on top of iptables. So you would base it on a Chef role instead of referencing other security groups or AWS attributes. And we gave a custom LWRP within Chef, which is essentially like a DSL entity, right? DSL declaration, in order to kind of create these iptables rules out of Symbolic Policy. And Chef would run and crunch these declarations and kind of translate those into computed iptables rules underneath. So you really wouldn't have to need to know any of the IP addresses or anything like that. Chef would figure it out for you based on these declarations. So this is an example of what one of those declarations looks like. This would be executed on a web server in order to allow access from a load balancer. So this kind of work that we did provided most of the flexibility we needed in terms of access control. It gave us all those really, really nice security group semantics, but outside of AWS and cross-region. So with the access control problem mostly addressed with this work we did, we wanted to turn to kind of a similar problem that we had with privacy. It's like iptables. At the time, privacy was like all wired up by hand. It was applied where it needed to be by a human. There was no kind of automation around it. There was no anything like that. So what we really wanted was like blanket encryption, just encryption that was easy to use and just worked out of the box. Like we don't want the developers to worry about, is their stuff encrypted or does it need to be encrypted, right? And in order to solve that particular problem, the most common solution that you find is VPN. Except the PagerDuty architecture means that VPN comes with a few additional challenges. One of the challenges is that VPN, like typical VPN architecture, uses site-to-site tunnels. And because the PagerDuty infrastructure is active-active, it means we have a whole lot of crosstalk between data centers, and these tunnels will be very, very heavily utilized, right? Which brings scalability and availability concerns on those particular tunnel heads, right? VPN heads, concentrators, some people call. I mean, you can look at the diagram and you can say, okay, well, that's one box, right? How many do I need there? How do they fail over between? What do the routes look like when that happens? What about health checks? What about this? What about that? There's a lot of complexity comes in trying to just manage that kind of a thing. So in addition to those pains, right, we had other pains too, which is like we're across multiple providers. Some of them don't provide VPC-like functionality. So there's no control over a private network, no control over the routing tables, anything like that. So in those kinds of networks, you're forced into a hub and spoke model if you take like the VPN route. And you can see I gave like a little example down there where with the lack of control over routing tables in a private network, you kind of have to have every client dial into the VPC heads, which are in that particular data center, in order to gain connectivity to the remote networks. So all these things combined gave just a lot of overhead in terms of availability, scalability, performance, and just like manageability, really, of the VPN model at PagerDuty. So, and the craziest part was, we didn't really even care about this whole fancy routing and overlay thing. All we really wanted out of it was the security stuff, right? Like all the nice security that comes with having strong VPN between all the hosts. So instead, we decided to drop the VPN part and just keep the IPsec part. So we ended up deploying raw IPsec in what we call transport mode, which means essentially all the security applied without any kind of overlay network on top. And it was configured as full mesh between all the nodes in the PagerDuty infrastructure, and those links would turn up opportunistically. Okay. So the network went from looking like this kind of VPN connected multi-data center architecture to something more like this, where mutual authentication occurs whenever the first packet is sent, and encryption gets applied transparently from then on. There's no gateways, anything like that. And additionally, the kernel is configured to drop all non-IPsec traffic. So if a packet comes into the kernel and it is not part of a known IPsec association, it's just dropped and nobody pays attention to it. So with this kind of setup, you get all of the benefits of VPN, strong VPN security, and none of the drawbacks of VPN itself. And so through this IPsec work, we got the confidentiality. We also got access control, who had strong access control through all the iptables automation, and additionally some good access control through IPsec itself, which is able to negotiate cryptographically rather than just based on IP addresses, right? But you put the system together, and you take a step back, and the whole thing exhibits some interesting properties, I think. So one thing that we can assert about this network is that all flows are authenticated and encrypted, right? I can say for sure, any flow that is occurring between applications on my infrastructure have definitely been authenticated through IPsec and are definitely encrypted by IPsec, right? I can also assert that all flows are authorized because we have this automation which is constantly validating that all the security configuration is appropriate and everything that is actively flowing has been just like kind of passed all the checks. And we can go and introspect those things and compare them to the policy we have codified to get a really good, strong understanding, like we know exactly what's there, no more, no less. And lastly, on this point, there's no inherent value in IP address. So it's not like this subnet over here is the web server subnet, and this subnet over here is that subnet. So we move further away from kind of like that old school network segmentation model and think more kind of along the lines of like, okay, well, which hosts are a set of this thing that we want to know about, right? So we do expose the IP address in some spots, but usually the places where the IP address is exposed is only for compatibility purposes, like in the enforcement layer. Like the enforcement layer might concern itself with IP addresses rather than attributes. So we expose the IP addresses, but there's inherently no value. Oh, it's gone. Inherently no value in those things in terms of like policy. How do I do this, Doug? All right. Sorry about that. It's not my computer. But perhaps the most interesting set of properties the system has is that there's no centralized firewalls. No centralized firewalls, which is really nice. There's no network gateways, which you're pinning a bunch of traffic through. There's no private network in which maybe firewall rules are less strictly applied in those cases than others. So you're kind of devoid of all these network control mechanisms that you see on a normal perimeter network, so to speak. And so after having built all these components and seeing how they work together and all this stuff, you kind of realize that essentially we succeeded in building a relatively secure perimeterless network in the public cloud. And it was around that time that we made that realization that BeyondCorp paper's first paper actually was released by Google. No? There we go. And this paper described Google's perimeterless architecture on their corporate network. And essentially, they'd been working on this thing for a number of years by the time they released this paper. This was in, I think it was like 2014, I think, they released the first paper. And there have been a series of papers released since then, which kind of describe this unmanageable corporate perimeter at Google. And essentially this story of, well, it grew too large, it's too permeable. We have hundreds of thousands of people coming in and off Google campuses each day. Some bring their own devices, some don't, some do this, some do that. And after a while, you kind of realize, well, this model, like given today's use cases and workflow patterns, right, is super ineffective at securing like against modern day threats, right? So it was really exciting for Doug and I to kind of read this work because it echoed a lot of the same principles and philosophies that we were kind of trying to address with the networking stack that we built at PagerDuty. So it validated a lot of the early PagerDuty decisions, security decisions, and not only validated them, but demonstrated an additional use case to us, which is essentially, like that client side of the use case, right? Versus what we had been focusing on, which is all like server-to-server connectivity, which is a whole different beast, really. And so that broader application of similar philosophies allowed us to kind of understand the full scope and implications of this model that we had been operating under. And we now call that model Zero Trust. So with those realizations and kind of a little bit maturation of the model, given the work and insights done by the Google folks, Doug and I gave a pair of talks about the model itself and the reasoning behind the model. And shortly thereafter, we were given an opportunity to write a book about it. And the amusing part is that neither of us actually really like to write. But we viewed the opportunity as kind of a mouthpiece because there's not a lot out there about how to actually build a perimeterless network, how to go about building a system which can be trusted but still operating in an untrusted network. So he took the opportunity and kind of ran with it. So with that, I'm actually going to ask Doug to speak a little bit. He's going to talk about the model itself and about the book.
All right. Thanks, Evan. Yeah. Everyone can hear me all right, yeah? So I'm Doug. So I want to talk to you guys about what we've learned as we've been writing this book. Sorry about that. What we learned as we've been writing this book, we've been working on this for a little over a year. And as you explore that space and talk to a bunch of different people, you learn a lot of lessons that I think are applicable even without necessarily doing the full model, or maybe gives you a better sense of what you're getting in this book. So probably the best way that I've learned to explain what Zero Trust is to folks is that we just want to assume in our threat models of our network that the internal network is just as hostile as a public network would be. Traditionally in a perimeter network, you would say that the bad guys are on the outside and the perimeter's job is to keep them over there and our internal network is trusted. Zero Trust says we've tried that, it's failed. We need to just make the assumption that we are always potentially having someone hostile in our internal network. And so since we're assuming that the internal network is as hostile as an external network, as much as possible, we want to architect systems that remove trust from that network. And so this ends up being fairly similar to how you might architect internet systems. So if we're gonna say that the internal network is untrusted, what does that end up meaning from our network architecture? Primarily, it ends up meaning that you can't use network position as a means for authenticating and authorizing traffic inside your network. Normally you might have something that says this, these sets of hosts, the fact that someone can even communicate to them because they're running on a private network means that must be authorized. Zero Trust would say, no, that's not sufficient. We need something stronger than that. And so when we say that, now we have to change our network security architecture pretty dramatically. Kind of like the PagerDuty model, like Google BeyondCorp, we need to authenticate and authorize every single interaction on the network. And the way that we found that's a good way to think about that is that we're going to be authenticating and authorizing users, devices, and applications, depending on the communication flow. So doing this also then means that there's a few other like additional constraints or ideas that come into this network design. The first is that as much as possible, we don't just want to rebuild like a virtual perimeter and say like, oh, well, we're all like, we're all buddies here on the network. Like this is all authorized, right? We actually want like least privilege pushed throughout the system as much as possible. And that's where that whole like, knowing what flows are flowing through helps you do that. Another interesting characteristic here is a perimeter network normally might, especially a physical one, you might have the firewall that actually does all the enforcement of your perimeter. But in a zero trust network, you tend to move away from having a small number of large firewalls and towards a large number of very small firewalls, because these like firewalls and infrastructure components are actually how you enforce the actual like flow, expected flows that are occurring in your network. And so when you take all this together, I think there's the final like kind of the interesting thing here is that this ends up being like a forcing function towards distributing enforcement throughout your network instead of centralizing it. Most network security would talk about like trying to get all traffic to flow through some security or network teams controlled infrastructure to actually manage access, whereas this would say, if we're going to have many, many firewalls, they're going to go throughout the network, and in like kind of a logical standpoint, they're closer to the host than a traditional network might be. Hopefully that makes sense. So I mentioned it before, but we're going to say it again. Like in a zero trust network, every flow is completely expected. And we're not trying to give people a network that they can just do whatever they want on, and then we will come in later and try to apply filtering. We need some mechanism for us to capture all expected flows. And if we have this like database of expected network communication, then we get the opportunity to really explicitly authorize every single communication and build ourselves a network that just makes the assumption that if it's not expected, we're going to drop it. There's an interesting like kind of detail here, which is you might think that, okay, well that means we will never have any unauthenticated traffic on the network, but that's not entirely true. You may have situations where communication is occurring, say like a user isn't authenticated. That is still modeled in the network, but it's treated as an exception that is routed off to a different system. So, maybe a user has to go authenticate with a single sign-on system, or kind of even more interestingly, devices can be unauthenticated. You could have like a new laptop that needs to be provisioned and imaged. And so we need to have our network policy say, well, if this is unauthentic device traffic, then it goes to the imaging service to actually get into a proper state where it can join the rest of the network. And so these policy definitions are extremely important in a zero trust network, because that's how we know where what flows should be occurring. And an interesting thing about what we want in that policy is, unlike say a perimeter network where you might define policy in terms of like physical network addresses or subnets, in a zero trust network, what we want to like arc towards is something that we like to call symbolic policy. So the idea here is that we don't want to describe our policy in terms of network primitives. We want to describe it in terms of like the logical things that exist on the network. And from that policy, we can actually go infer the enforcement rules. And this gives us some really great properties. We can define policy that travels with what's called like the workload, right? The application that's running in the system. And if we know where those workloads are running, we can reconfigure control systems automatically to enforce the policy that we've captured elsewhere. So both like, this isn't like concrete pie in the sky stuff. Like both PagerDuty and Google define policy in some sort of symbolic format. And we both ended up, interesting enough, using DSLs, domain-specific languages, to define that policy. And then that policy is pushed into enforcement systems. In the case of like Google, it's pushed into what they call like their access proxy. In the case of PagerDuty, it's like distributed out through the entire system. But having a DSL isn't mandatory for a zero trust network. I think just the key idea there is that policy is separate from enforcement. And from a good symbolic policy definition, we can calculate and configure enforcement systems. And to make this something that might be a little more concrete for systems you use today, I would argue that when you look at it and that like policy is separate from enforcement, Amazon security groups are a great example of symbolic policy where the actual like physical checks are just abstracted away from you, right? Like if you ever, if you were to build a zero trust network, or if you were to define that like application load balancer interaction, you would put the app servers in one security group, the load balancer in a different security group, and you would configure the app servers security group to reference, logically the load balancer security group. You're not enumerating individual IPs or subnets. You're thinking about it at a higher level of abstraction. So we talked about like we need to authenticate and authorize users, devices, and applications. But we need to be really careful that it's just authentication of those components that we're using in a zero trust network. And when it comes to authorization, auth-c, we're actually authenticating the combination of all three of those things in time and to make a policy decision. So we wanted to give this thing a name because I feel like right now when we talk about network security, we tend to talk about each of those three things we can see, and we don't talk about like this abstract idea of when we take it all together and put it in context, what are we authorizing? And so we gave it a name. I don't know if it's the best name, but we're calling it a network agent, kind of trying to echo like the idea of a user agent for a browser. So this is the combination of user, device, and application, and it's what we use to make authorization decisions. We would actually prefer that policy is written referencing attributes of the network agent. And so when we do this, it's not just for semantics. Like we actually get better. We are better able to craft policy that describes our intent. So I work at Stripe. One of the interesting things that I see even in Stripe systems is I, as an authentic user of Stripe's infrastructure, have less capabilities on my phone than I do on my laptop. I can say check my email on my phone, but I can't like commit to source control. And if you were to try to say, well, we're gonna treat each of these authorization decisions separate, like we're going to say this is an authorized device and this is an authorized user, I don't know that you could write policy that actually captures that my fully authenticated self on my fully authenticated phone has lower policy than my fully authenticated self on my fully authenticated laptop. And so that's why we want to like get this idea out that you need like a network agent, and you write policy against network agents, not against individual users. So, if you think about how you might do this in most systems, like actually implementing a zero trust network sounds great, but it also sounds incredibly toilsome. Like you could imagine just people spending all day, every day trying to reconfigure control systems. And so the key like enabling change that allows us to do this is just pervasive automation in IT systems nowadays. If we can fully automate the configuration of control systems, then we get to do things that previously were kind of unrealistic. You even see this in PagerDuty system, right? Like a mesh network is not a new idea, but it was generally put off as being unrealistic because you have to reconfigure the entire system. Well, if we have an automation framework, which I would argue that in a lot of systems is your configuration management framework, we can do some unreasonable things and actually automate the entire system's configuration. And so when we take that policy, what is essentially a policy database, we shove it through our automation framework, really what we're doing is we are continuously reconfiguring our system to realize this abstract policy in like the actual implementation details of the system right now. So if we move an application from one server to another, we want the automation to just reconfigure the system and still affect the same policy that we inspected previously. And if we don't have that automation, then we're going to like eventually sacrifice that desired invariant. So it's very important that like automation is the cornerstone of how you can build a zero trust network. But these are all like enforcement ideas, and I think zero trust is not just about really great ways to enforce traffic. It also gives you some benefits. I was in the Envoy talk just before lunch, and there's some similar ideas here, right? Like Envoy as a base infrastructure that's provided in your system gives you really great visibility. Zero trust feels like Envoy kind of echoes that idea, where we want really deep visibility into the network communication going on in our systems. And we want this for a few different reasons. One is risk analysis. We want to make sure that we're building like a least privileged system, and the way we do that is we inspect the flow connections that we have through the system. but also for forensics. Like as anyone who's done security knows, like eventually there will come a scenario where you have a security incident, and your ability to figure out what happened and be able to say with certainty that you've closed whatever hole someone used to get in is extremely important. And by having all of your network communications so well codified, it really helps with that forensics problem. And the Zero Trust model uses infrastructure to reconfigure itself, but that same infrastructure is really well positioned to give you this great visibility. We could add hooks for logging or eventing, and just have much deeper network visibility and better security in our networks. And this policy database can also be used to help drive down a lot of the noise that you might have when you try to impose really rigorous definitions of what network communication should occur. We can use that database to validate connectivity or validate unexpected flows, update it, and keep our system running. A good example here would be like if my corporate laptop starts doing things that are odd relative to the policy that I have defined, we can use that as a signal for alerting. And this visibility system also ends up being like the source of data for more advanced ideas in this type of network design. Like we like to talk about using machine learning to help drive alert configuration. Well, the first thing you need if you want like a machine learning system is you need really rich data of actual flows, and you probably need some really good way to define what is expected. So this like visibility system is going to end up helping us create a feedback loop that keeps the system running. And so if you're like building a system right now, if there's one bit of advice I could give you is to start early capturing this data as much as possible. We've talked with people who have large networks that they recognize that the security is not as good as they expect it to be, but at that point they've added so many different interconnections that like the entire idea of trying to enumerate every single communication flow is just unrealistic and won't happen. And so when you're starting small, you have this opportunity to start capturing this data and keeping it up to date over time, and that way you kind of amortize the pain of having this entire network communication database that tells you what you should expect. It's a lot cheaper if you do it earlier. So definitely start capturing it earlier. But you don't want it to just be some database that it doesn't reflect reality. So a really good way to keep it up to date is to try to integrate it into your enforcement mechanisms as soon as possible. So in our system previously at PagerDuty, that ended up meaning that we, as a team that was providing the network services, would push back against people wanting looser rules and say like, no, we need to enforce these things because it's getting us a database that's going to give us value down the line. Enforcement doesn't have to mean that network communication doesn't flow. It could just mean that someone's alerted and actually updates the database. It's up to you on whether or not you want to do that. But we have to be careful here that enforcement does not necessarily mean that we're breaking applications or causing other engineering teams to slow down. So if you're interested in this idea, you might naturally be curious, like how do you what's the current state? Can I do this today? So right now, unfortunately, Zero Trust is kind of still mostly a roll your own solution. If you go talk to a lot of these companies, you'll learn about them doing ideas that are a little bit there, and they've got like this little piece here and that. And so there is like a general trend towards like something that is repeatable. And we want to share with you some of the companies and stuff we've learned about and projects. But the reality is today, it's not going to be as simple as doing a perimeter network. But the nice thing is that this is all just like, pre-existing tools and building blocks. It's things you're used to. It's not a crazy idea that, is just magic that'll make your system work. We just need to put those tools together in a new way and really wrap really great automation around them so that we get a better network model. And as you might guess, this is, a new idea. It's very large. It's complex. So there's really a lot of opportunity for getting your hands in and helping define what could be like a new network security architecture for the future. And so we'd love your help with that. And so with that, I'm going to pass it back to Evan. He's going to share with you some like logos and projects that you can go learn more.
Thank you, Doug. I don't need that thing. Yeah, so as Doug mentioned, Zero Trust is still very much roll your own. there is no end-to-end solution. There are some commercial options. We think it makes sense to kind of just go over kind of what's going on in the industry and in that context. So who's doing this? Both corporate and commercial, right? Before we jump into that, I think it's important to kind of just make this distinction that we see this divergence, this kind of two modes of the zero trust model. We see one that is kind of a client-side mode and one that is a server-side mode. And when I say that, I mean, are we talking about client-to-server communication such that you have clients in the field which are communicating to centralized resources? Or are you talking about servers within a data center, service-to-service traffic, what some people might call east-west traffic? And those two, they end up being quite distinct models just because the nature of the communications of those two things are very different. Clients behave very differently than servers do. You have a lot more control over servers than you do on clients, et cetera, et cetera. So you make different trade-offs on those two deployments, right? But in terms of, so we'll specifically kind of focus on each one of those, right? So in terms of client-side deployments, we have companies like Coca-Cola, Mazda, and Google. Google, of course, with BeyondCorp. Coca-Cola and Mazda both leverage a technology called software-defined perimeters, which is a Cloud Security Alliance emerging standard that kind of defines how a client in the field anywhere in the world can connect to a secure enterprise resource and following the zero trust model, if you will. Coca-Cola does it for rapid provisioning of branch offices. They do it so when they have a new branch office, they can turn it up in one weekend. They don't have to worry about reconfiguring VPN connectivity, giving them credentials, setting up all the firewalls and all this other stuff. They treat it as a regular internet connection with public Wi-Fi hotspots in the office, and everyone just goes to town. And Mazda, in a similar fashion, they use it for their car fleet, all the cars they have in the field, which have all sorts of sensors and computers on them, all phone home with telemetry and other kinds of things, and they provide value-add services for Mazda customers and things like that. And they secure that fleet of clients, if you will, using this zero trust-like technology called SDP. Google, rolled their BeyondCorp solution for the purposes of simple raw security and scalability. They wanted to protect production from corporate and vice versa, and also wanted to let their corporate employees roam free. So this is a really attractive option for them. And on the server side of things, we have companies like Square, Lyft, PagerDuty, Docker. And similar to Google, most of these companies have adopted zero trust model within their networks, primarily for security and scalability purposes. If you've ever used Docker Swarm has a connectivity model that is very similar to kind of the zero trust model with mutual TLS throughout. But again, all these companies, these in the previous slide, they've all rolled their own solutions. None of this stuff is out of the box. None of it is, let me just install that package. There are, however, some commercial options to achieve like similar semantics, right? So we have companies like Apparito, Calico, and Illumio, working on zero trust problems in the data center, like the server-to-server problem. How do I dynamically update policy? How do you define that policy? How do you attach it to things that move around? And how do you actually affect it? We have companies like CryptZone, Vitter, and Waverly Labs who are working on zero trust technology on the client side, leveraging mostly that software-defined perimeter standard that I mentioned earlier. And then there's a company called ScaleFT and Duo who are working on also client-side zero trust by way of kind of BeyondCorp style implementations. So all of these vendors provide zero trust style components, right? But there is still no like end-to-end solution, and none of these things are like mutually exclusive with each other. You still kind of need a combination. You need to do some here, some there, and some over here, right? So to take this all together, and you take a step back, as you can kind of see that hiding behind the perimeter is pretty bad. Like it undermines a lot of like really good security hygiene that you would normally have otherwise. And we've seen that it's just like ineffective, right? And the industry is kind of moving as a whole towards really, really deep authentication and authorization in order to kind of compensate for the holes that are turning up in this perimeter model as threats change, the threat landscape changes and all those other things, right? So we think like we see the industry kind of converging on this zero trust model. It's kind of happening already with the various product offerings that we're seeing and kind of the talks that are being given and stuff like that. And some of these products and offerings are like more ambitious than others, but like I said earlier, it's likely going to be manifested as like a collection of systems. There's a lot of responsibilities and things within a network that must be dealt with, and it's unlikely that a single system will handle all of these concerns and responsibilities very well. But in the end, you end up, like if you actually do achieve that, you end up with a more secure and more operable system as a whole. So keep an eye out. Things are popping up like brand new every week. Things are happening in this field. It's very, very exciting, very, very new. Doug and I would love to talk to you more if you think this stuff is interesting. You know, we're looking for people to help hack on stuff with us. We're looking for people to help give talks. We're looking for everything, really. So we'll be around here for a while. We'll be here all day. And I think we're going to open up for questions because that's all I've got. And thank you for your time. We have a mic if anyone has any questions. OK, thank you very much.